He reads it, goes to Laplace and says, Monsieur, this is a beautiful piece of work, brilliant, but you make no mention of the architect of the system. He's referring to God. And Laplace replied, sir, I had no need for that hypothesis.
Ooh, that's a mic drop. Ooh, that is tough. Man.
That's a dig on Napoleon and on Newton.
Yeah.
And on Newton.
I have, oh man, look at that. Yeah,
all right. So let's keep going.
Go ahead.
So now, let's say we have not just the planet and one of its moons, but let's say we have a star and another star, double star system.
Right.
Famously portrayed in what film?
Star Wars.
Star Wars.
Yeah.
All right, of course.
Here, Neil deGrasse Tyson is talking about how a great scientist once told a powerful ruler that his model of the heavens had no room for an extra, untested explanation. That line wasn't bravado. It was a statement of method. In science, every idea must pay rent in the currency of prediction. If adding an assumption doesn't change what you expect to observe, you don't throw it in the trash. You simply set it aside until evidence demands it. That's not a dismissal of wonder. It's respect for reality's right to veto our preferences. Take gravity. One planet orbiting a star is an elegant waltz. Add a second star, and you'd think the dance would descend into chaos. But gravity is democratic. Every mass tells space-time how to curve, and every object follows the curvature. When astronomers study double-star systems, they find two main neighborhoods where planets can live. Either a planet clings close to one star, with the other star far away, or the planet orbits both stars at once, circling their shared center of mass. Those arrangements are not guesses. They drop out of the equations and are confirmed in the sky. You might remember the fictional double sunset that fired our imagination. Nature beat Hollywood to it. The Kepler Space Telescope found planets orbiting real binary stars, the first was Kepler 16b, by watching the starlight dip as the stars eclipse each other and a planet transits across them. The timing of those dips is so precise that we can predict when an eclipse will occur years in advance. No additional actors required, just gravity, geometry, and a telescope with a steady stare. But here's the plot twist. Add one extra body to Newton's clean two-body problem, and mathematics no longer hands you a tidy formula. The three-body problem is famously resistant to closed-form solutions. System can become chaotic, highly sensitive to initial conditions. You don't get cosmic anarchy, but you do get vulnerability to tiny uncertainties in what you measure. That's not failure. It's an upgrade in honesty. We trade exact formulas for numerical simulations and statistical forecasts. And look who pioneered that mathematical toolkit, Laplace himself, who helped build probability theory. He envisioned perfect knowledge yielding perfect prediction, yet the universe showed us that determinism and predictability are not twins. The laws can be exact while our forecasts are probabilistic. So how do we decide what belongs in our models? We use a principle older than any telescope and sharper than any mic drop. Don't multiply assumptions beyond necessity. Today, we even quantify that discipline with tools like Bayesian model comparison or information criteria that penalize complexity unless it improves prediction. When Kepler data show starlight flickering just so, astronomers test a suite of models. Is it a single star with spots, a grazing eclipse by a companion star, or two stars plus a planet? The winning model isn't the one with the grandest story. It's the one that best fits new data while adding the fewest moving parts. That's the practical meaning of no need, not an ultimate verdict, but a provisional ruling grounded in evidence, and the universe keeps giving us chances to revise that ruling. We didn't want to add dark matter to our cosmic ledger. It arrived as a debt we could not ignore, demanded by galaxy rotation curves, gravitational lensing, and the growth of the large-scale structure. Dark energy wasn't a poetic flourish. It was forced on us by the measured acceleration of the expanding universe. Extra hypotheses can join the party, but only with a valid ID. They must explain what we observe better than anything else on the table. That's the same standard that tells us when we don't need an extra hypothesis at all. There's a human side to this. When early astronomers found order in planetary motions, it felt natural to anchor that order in a guiding intention. Later, we discovered that intention wasn't necessary to account for the motions themselves. That can feel like a loss. But consider the gain. We learned that invisible rules, written in the language of mathematics, are stable enough to choreograph entire solar systems, even double-star systems with planets that endure for billions of years. Our place in the universe didn't shrink, our reach grew. We learned to calculate eclipses in binary systems, model their climate zones, and even estimate whether a rocky circumbinary world could host liquid water. The laws are not cold, they are reliable, and reliability is what lets curiosity grow up into knowledge. Here's the real cliffhanger. No need is a moving target. As instruments sharpen and data accumulate, what was once unnecessary can become indispensable. We might find that some exotic new field or particle is required to explain a subtle precession in a binary's orbit that survives every conventional check, or a faint frequency-dependent dispersion, or extrapolarization in gravitational waves as they traverse cosmic distances. If tomorrow the universe insists on a new ingredient, we'll welcome it, not because it makes us feel better, but because it wins the audition against the evidence. So, when you hear that a scientist found no need for an extra hypothesis, don't hear contempt, hear calibration. It's the discipline that keeps us from stapling our hopes onto our models. It's what lets us map the dynamics of double suns, weigh unseen matter, and trace the story of cosmic expansion. All with the same simple rule. Ideas must change what we expect to see. That is how science honors both humility and ambition. We ask the universe a clean question. We accept the answer, even when it slashes a cast list. And we keep watching, because the next update to necessity is always one better measurement away. Like if this was interesting, and hit the subscribe for more.